All right, let's make a start. We have quite a bit to cover today. So as always, I'm just going to remind you, sorry, what we did last week. Also going to remind myself where we were, and then I'm going to tell you what we're going to do today, which is quite a bit. But last week we talked about taxation, and we showed that taxes brings about static efficiency. So just to remind you, static efficiency, we're talking about that we get the desired level of pollution at the least cost. So we move from E-private to E-efficient at the least cost possible. And we also talked about dynamic efficiency, right? We said that, anyone remind me what dynamic efficiency is all about? What is dynamic efficiency? Over time, we give firms, yeah, that's exactly the case, right? So over time, we also tax provide firms with some incentive to innovate, as you said. It looks like a great proposition to impose a tax, and we also talk about other aspects, potentially the double dividends, but also about some of the issues with imposing tax. We had, I think, quite a long discussion around distributional aspects, tax regressivity, and all these kind of different things. All right, so we talked about all of that. We also thought about taxation. We said like why we might prefer subsidies over taxes, and why we prefer taxes over subsidies. So taxes, with compared to subsidies, we economists prefer them because they're always kind of the efficient options, and we said that tax and subsidy don't necessarily yield the same outcome. So in the short run, we had two, if you remember, two cases. One, that we have homogeneous firms, so all firms the same. We showed the taxes and subsidies behave in exactly the same way in terms of, yield the same outcome. But then we show even in the short run, if we provide a subsidy, we get different result, tax still efficient, subsidy. We essentially going to subsidize inefficient firm that should be out of business, frankly. And then in the long run, that's definitely a big issue. It's not just that we keep inefficient firms in the market, we also potentially provide incentive for inefficient firms to enter the market, right? So we got very different results here. And so this is why we kind of prefer taxes, but also we talked about the other issues that we mentioned, including, if we want to go with a subsidy, where we get the money from, things like that. But in terms of why sometimes we go with subsidies, we're going to talk more, you guys are going to talk more about when it kind of makes sense to use subsidies, actually, towards the end of the second term. But we also said that sometimes we kind of need subsidy because we can't use taxes for political reasons, for example, things like that, right? So this is kind of what we discussed last time. What we're going to do today, we're going to do three things. One, we're going to do command and control, something that just ran out of time last week, so I'm going to go through that. Hopefully it's not going to be too long. It's kind of straightforward, I think. We're going to bring the figures that we had last time, and I'm going to show you how command and control is something that in most cases I'm not a big fan, and I'll explain to you why. Then we're going to spend quite a lot of time on tradable permits. How does that work, and how that is potentially somewhat similar to taxation. We're going to talk about it in terms of static efficiency, dynamic efficiency, and all the things that we mentioned before. And then kind of, I guess after the break, or maybe a bit later than that, we're going to talk about some issues. We're going to start to relax some of the assumptions that we implicitly had throughout. Start relaxing some of this assumption and see how that might complicate our analysis, okay? And specifically, we're going to talk about spatial and temporal dimensions, so how space and time actually has an impact on our analysis, okay? We're going to do it relatively, we're not going to go too much into that because we're actually going to cover both of these things in greater detail later in the course, all right? But we're just going to look at how these things directly affect what we've done so far here, okay? Just to kind of make a start and make us think about how things actually look like in real life. So let's start with command and control, also known as directive or mandatory regulation. Historically, it's the dominant form of environmental regulation, and still probably the one that's used most often. Two defining feature here: command what the regulated party must achieve, and control a penalty or a sanction for non-compliance with the regulation. Now, there are two types, broadly speaking, two types of command and control regulation. The first one is technology standard. This is when the government or the regulator tells the firm, for example, exactly what they need to do. So they specify a particular type of equipment that must be used. Let's say you just have to put a certain filter at your plant or something like that. This is what we mean by, we say, technology standard. Performance standard is something slightly different. We're going to think more about that because at least you have some kind of, say about how you want to do things. But basically, that just, when we talk about performance standards, it just stipulates the maximum emission that are allowed per unit of economic activity, something like that, okay? So it leaves some flexibility with the producer, okay? So it's similar to economic incentive, but it's not quite the same. There is a restricted choice for the polluter to as to what means they can use, to be completely honest. But the main point is that it doesn't have the machinery to get the equal marginal principle, what we talked about last week, which is the condition for cost efficiency, okay, to basically equalize the marginal saving across the different polluters, which is, remember, we showed it last week, graphically, mathematically, and we talked about it, why this is a requirement. And basically, I'm going to show you that now. With command and control, we don't get that. So this is kind of the big issue here. Okay, don't worry if you don't really get what I'm just saying, but I'm going to show you that on a figure just now. Right? So the definition, the official definition, or something like that for command and control regulation involved the environmental regulator stipulating the action that an individual firm or polluting facility should take with regard to pollution control or other environmental protection through the firm, though the firm may have some limited flexibility in how to meet the regulatory requirements. Okay, so let's kind of go back to the figure, similar figure that what we had before. So what do we have here? We have the economy-wide marginal damage function, the MDC, marginal damage cost, and then we have two marginal abatement costs. Okay, let's think about, we have two firms. Okay, two firms have different marginal abatement costs function, MAC1 and MAC2, and we can also create the economy-wide marginal abatement cost, which is basically going to be this line here, okay, with horizontal summation. So it's the MAC1 plus MAC2, so it's go all the way here and here. Okay, and we know what is the efficient level of pollution, which is just at this point in here, and we know what is the market outcome. The market outcome going to be here, right? When we don't internalize the externality, we don't care about the damages. We're not going to want to invest anything in abatement. So basically, our abatement cost is going to be equal to 0. This is what E-private here actually means. All right? So our aim here is to move from here to here. Okay, this is what we're trying to get. Okay, so let's say that if we want to move from here to here, we need both firms to reduce the emission by a certain amount. Let's say that each one of them need to cut it by, I don't know, their emission by 20%. Seems fair. You know, it's kind of the same amount of pollution for same amount of pollution reduction to each one of them. Basically, they're just going to move it from B to A. Okay, let's say something like that. Okay, and if we move from B to A for both firms, we essentially have enough to move from E-private to efficient. Is that efficient? Yes or no, in terms of static efficiency. Let's look at what's going on here. Okay, again, not discriminate anyone, I'm not doing anything. I've just said both of you cut the same proportional, right? The same proportion of emission, right? They both start at B. So you both need to move to A. What we're going to get? So both of them moving to A, okay, from B to A. What's the marginal abatement cost at A for these firms? Is it the same? Different? What is it? Different. Why? Exactly, right? Absolutely. So for firm 2, the marginal abatement cost is here. And for firm 1, the marginal abatement cost is here. So if we do that, if we basically said to both firms, cut it by, let's say, 20%, whatever that is, then we don't get cost minimization. We might get an effective policy in the sense that we move to E-private to E-efficient, although that will require a lot of information to be able to tell you exactly what's the percentage reduction that is required. especially if we're talking about lots of polluters, right? But let's say that you can do that and it's not that problematic. We don't going to get cost minimization, which is our definition for efficiency in terms of the policy, right? We want to move at the least cost way from e-private to e-efficient. We don't have that because for cost minimization, we needed a marginal abatement cost going to be exactly the same. We don't have it here. So it's static inefficient command and control. This is why I don't like it. And it's not just, it's what, remember when we talked about taxes, we said like, look, it's not just about abatement costs, right? It's not that we essentially want firm one to do most of the abatement because it's just cheaper for them to abate, right? But here we don't use this, right? We basically ask them to reduce their emission by the same amount. So it's not really efficient. That's the point. Okay, with the taxes, it made sense that firm one reduce more because they're trying to save on the taxes, right? Don't forget, polluter pay twice with taxation, right? Here we don't have this mechanism. That's the point. All right, so it's static inefficiency. There is no this kind of invisible hand that kind of drive them to the efficient outcome that we want. Doesn't exist here, okay? In a way, we're going to talk about tradable emission permits. I would argue, maybe I should have done it at the end, this is kind of a non-tradable emission permit, in a way. And as you will see very soon, the trade is what make, cap and trade efficient. It's all about a trade. And here we're just like, look, this is what you have, you can't trade, pretty much. So to me as an economist, that doesn't make any sense. Having said that, this is what we use most of the time, all right? We can talk about it in the seminar why, potentially, okay? Okay, so it follows the equal marginal principle, meaning, it's essentially impossible to equalize marginal abatement cost, so it doesn't really work, okay? It just generates just much more expensive option for policy. I'm not saying that you should never use that, sometimes you should, but, often cases you should. Okay, what about dynamic efficiency? Again, you told us, thank you very much before. Should get stickers, give people. But I'll give you next time. But what about dynamic efficiency? Basically, if we provide incentive for innovation. So let's look at this diagram here, okay? So obviously, if the government tells polluter exactly what they have to do, when we talked about, technology standard, that's probably not going to help that much for dynamic efficiency. But let's assume that we are dealing with, the second option that we have here. Basically, they set an emission level, right? So it's kind of the permit situation that I mentioned before. So now we have, it's not two firms here. We have MAC1 and MAC2, but it's one firm. Okay, so let's start with MAC1, right? This is where they are. Now we're moving across time, right? So MAC1 is the current state of the world right now. The government decided they don't want to be here anymore, right? They want to move to E1, which is the efficient level at this stage. What's going to be the abatement cost for firm 1? Well, it's just going to be A plus B, right? It's moving from, it's the area under MAC1 from E private to E1, okay? Now, if the government doesn't change anything, does the firm have any incentive to move for something like MAC2? Conditional on the fact that E1 remain the efficient level of pollution according to the government, the answer is probably yes, right? Because, well, how much their abatement cost would be, well, now it's going to be B rather than A plus B. So it's actually less. So there is some incentive to move. By the way, if you compare it to what we did last week, the incentive is smaller, actually, compared to the tax. Remember last week we had more than just one of these triangles. But, it's also fair to assume, this is kind of, I think, very interesting, that government will update in some point their goal, and now that they know there is new technology, whatever, maybe the new desired level of pollution moves to E2. So what's going to be the case if it's E2 now? Let's consider that. So before with MAC1, it was A plus B. Now it's B plus C. So I don't know what is bigger anymore. I mean, C can be bigger than A under some conditions. So then I don't necessarily going to have an incentive. It doesn't have to be. It doesn't look like the case here. Obviously, we can calculate that, but I can totally draw it in such a way that it will be. Yes. Well, say again. Sorry. So you said it anyway. It's going to move to E2. Yes. Why? Why? It's only if they innovate, right? Because the E2 is only depends on the on the intersection of MAC2 and MDC. Basically, the level of the abatement technology that we have. So now we move to a different state of the world in which we have MAC2. We didn't have that. That came from innovation. By the way, what I don't show you here and what I didn't show you before, it's what is the cost of moving from MAC1 to MAC2. That's completely absent from this diagram. We're going to talk about it later on in the course when we talk about innovation. Don't worry, everything will come together. But that's another factor that is not here. Yes? It's not an assumption. Well, I guess yes, it is. It's a scenario in which, like, if you think about government and how they need to set the regulation, so they need to set the regulation basically thinking about the costs, right, and the damages, the abatement costs and the damages, and things change over time, right? So now we have, it's just cheaper we want that. Actually, as economists, we spend lots of time thinking about it. Why we want to incentivize firms to go from MAC1 to MAC2, because that really shifts the efficient level of pollution towards zero, which is something that we actually kind of want to. There are two different things, slightly complicated. If MAC1, this is the current state of the world, I don't want to go anywhere towards zero past this point here, because I need to balance, the cost and the benefits, essentially, right? But we totally, if it's MAC2, we totally want to move towards zero, right? Because just the abatement costs are much lower now. So we want, in the medium long run, we want to create this innovation. We want to be able to, generate the same level, even more level of economic activity with much less environmental damage. This kind of makes perfect sense, right? And that comes through innovation. We want to continue to drive our cars, but we don't want to generate NOx in central London. So we want firms to think about electric cars, and then the generation of electricity will come from renewable. We want that. And we want to be able to storage of renewable. We want that. It's going to be economically viable. We want all of that. We want to give this incentive, right? All right. So anyway, my point here is that it's relative to taxes or other, what we're going to show today, is just inefficient, dynamically speaking. It provides some incentive, depends on the situation, whether the government reacts or not, but it doesn't have the system that was built in the tax because of the prices. Prices are amazing, right? Remember what happened when the government intervened last time and said, like, when it was with taxes, and then it was the same thing, right? But then what happened, right? So we were here, and then the government intervened, and now we moved to here, right? From E1 to E2. What happened is that the tax rate dropped quite a bit. So then we had to pay less in terms of tax revenue. So it was actually beneficial for the firm. We don't have that built in here. That's the point. Remember that basically we said, like, does the government have, do the firm want to move to E2? Yes, because tax drop. Right? So we had two things with taxes. We had the payment of the tax plus the abatement cost. You might pay more in abatement cost, but overall you're going to pay less because you pay much less tax. Okay? That was the point. All right, I'm spending way too much on something that I really don't like, so I'm going to move on. All right. I'm joking. It's not that bad. Okay. Cons of command and control regulation. This is just a list. Pros. Yeah. I guess it's easier to monitor emissions, assuming that we're going to talk about monitoring next week. We're going to spend an hour talking about that. I guess it gives you greater certainty as to how much pollution will be emitted. That's what people argue, but to be honest, like even if you install something, let's say technology, it doesn't mean that you necessarily maintain it well. And I'm not sure if, and there is empirical evidence that show that they, sometimes firms don't maintain things well. And then that kind of, reduce the effectiveness of these instruments. By the way, lots of time when we get like, engineers kind of studies about how, let's say, a new cooking stove or an air purifier works in a lab, and then when you take it to the field, you get a completely different number, right? Because at the end of the day, it's people that need to use that. There is a behavioral aspect here, and they need to maintain it, whatever. So lots of things change when you test things in the lab and in the field. Yeah. Yeah, absolutely. We're going to talk about it next week, okay? Yeah, that's I mean, something like, nuclear stuff, right? So you want to be, if you make something slightly wrong, it depends on, we're going to talk about it when we're going to think about uncertainty around damages and abatement costs, right? So, you don't want to make a mistake, if the damages are so steep, right? But we're going to talk about it next week. But yeah, so this is why I said I hate it, but not all the time. Sometimes it makes sense, yes. Yeah. Absolutely. Maybe you just can't. Yeah. No, for sure. Sometimes you can't. You basically said like, in reality, you can't do that because of lack of institution or something like that can enforce something like that. Yeah, we're going to talk all about enforcement and all of this stuff next week. I'm trying to relax assumption as step by step, but you're absolutely right. That's a good point. So again, I'm trying to be a bit provocative. I don't know if you got my kind of vibe. In general, I'm trying to be a bit provocative. Please don't hate me. Yes.
Do you maybe have like one empirical but striking example for like one command and control regulation in the UK that
in the UK, okay.
Really, really bad?
I'm recorded. We can talk about it in the seminar.
Okay.
Okay. Yes. Okay. Bad regulation, my favorite topic. Yeah.
How the command control can disincentivize innovation as compared to regular tax. But with the carbon trading scheme, doesn't it have the same issue as the command and control where disencourages innovation as when innovation occurs, what you would do is reduce the available carbon rights?
Yeah, even better, let's do it. Okay. Thank you for the nice transition into cap and trade. Okay, so tradable permits, I think that I will answer your question in probably 5-6 slides from now. Okay. All right, so most general form, a tradable permit can be defined as a transferable right to a common pool resources, and one of the most obvious examples is transferable quotas for fishing right. It's, our focus today going to be on something more specific, which are tradable emission permits. Not something new, something that was proposed back in the 1960s by Thomas Crooker and John Dales. It's essentially a market-based instrument which combines elements of three main approaches to pollution control. So let me kind of go through what's going on here. So first, the regulator set the total quantity of emission. So in a way, it's kind of similar to command and control. So we as a regulator decide, okay, how much emission is allowed in our economy, let's say, and you know how to do it already, right? Because if you have the marginal abatement cost, you have the marginal damage, you can totally do that, right? So that's great. Then plants are assigned permits, or essentially the right to pollute, which is basically where the property right-based approach kind of comes in. So in a way similar to the cost theorem. But then the most interesting things kick in, which we basically allow firms to trade. Okay, and this is kind of what brings all the good stuff that I will show you now. So permits can be, we allocate, and we can talk about how we want to allocate initially. That can be a whole course, by the way, but we're not going to do that. We're just going to spend, maybe a few slides on that. You can read more. But once we initially allocate it through different ways, then basically firm can buy and sell their permits. Okay, this is really important. This is the economic incentive-based approach that is keen to get all the good stuff that we want. Okay, so different types. One is emission reduction credit, ERCs. A facility that does more than it's required under existing regulation receive credit for its extra efforts, and then credits can be sold to other facilities. So let's say that you currently, as a firm, emit 100 tons of whatever, you're required to reduce it by, let's say, 20 to 80, but you can also reduce it by more, by 30. The extra 10 you can sell to another firm. That's the point of that. And then what we're going to cover mainly today, which is something that it used more frequently. I mean, ERCs were used as well. I mean, example would be the phase out of liquid gasoline in the United States. That was ERCs. But what you probably heard before in terms of this kind of stuff is something like the EU ETS or the acid rain program in the United States. This is what we call cap and trade. So let's focus on that, and I'm going to show you some empirical evidence on the effectiveness. Not much about the efficiency for now of these two programs. I'm going to show you some evidence on that. Right. So what is cap and trade? Involve one, a decision as to the total amount of emission that is being allowed, that is to be allowed. Two, a choice over how the total quantity of permit is to be initially allocated between facilities. Do we want to give it for free? Do you want to auction it? What do you want to do? And then set up some trading rules. Okay? Quite straightforward. And let me show you how good this system is. Okay, this is just a quick preview. So under some conditions, okay, let me clarify that, the following results hold. In equilibrium, this is for cap and trade. Again, under some certain conditions. In equilibrium, marginal abatement costs will be equal over all firms. So we're going to get the equal marginal principle, which is our requirement for cost minimization. Fantastic. The equilibrium price in the permit market is equal to the Pigovian tax rate if we had used taxes as a pollution control instrument instead. So I'm going to show you how the permit price is going to be equal to T star from last week. And then if the cap set equal to the socially optimal level of pollution, allocative efficiency is achieved independently of the initial allocation of permits. Okay? So if you set it equal to the desired level of pollution, to the efficient level, then you're going to get efficiency. Okay? Because we know that it's going to be cost effective. If you set it to the efficient level of pollution, by definition, assuming full compliance, etc., you're going to get what you want. Okay, let's say that you want to move from whatever level of emission, let's say 100 to 80. If you just set the number of permits to 80, you're going to get that. Again, assuming full compliance. And it doesn't really matter how you allocate the permits originally. So let's look at an example. Let me kind of start showing you how it all works. Okay, so we have two polluters, A and B, with different marginal abatement costs. We talked about why different firms have different marginal abatement costs. Let's assume now that emissions are uniformly mixed together. And then the total emission in the absence of regulation is equal to this following thing. So E bar equal to the emission from firm A plus the emission from firm B, which is currently equal to 20. Okay? Now, you two here, you're smart, you took GY426, you already know that 20 is way too much. I gave you the marginal damage cost, I gave you the marginal abatement cost. You tell me, Sefi, 20 is too much. We need to move to 8. Thank you. All right, so we need to move from 20 to 8, all right? That's going to be what we call the cap, all right? And if this is, and I trust you to do the calculation correctly, this is the desired level of pollution. So if everything works perfectly, we should get the efficient level of pollution. Okay, because we just issue 8 permits, and each permit can give you the ability to emit 1 ton of whatever, let's just say, okay? And let's say that just for fun, we decided that we have 8 permits and we're just going to allocate them equally across these two firms, 4 and 4. Okay? It will never really work with two polluters, which for reasons that will be which become clearer later on. But for the example, it's absolutely fine. Okay, so let's look at these two polluters graphically and look how it looks like. So on the left-hand side, I have polluter A. Okay, so that corresponds to marginal abatement cost A. And then on the right side here, I have polluter B, which corresponds to marginal abatement cost B, right? And it's easy to kind of, to draw them. You see it's a linear, it's a straight line essentially from the marginal abatement cost function that I gave you here. And you can, for example, you can think about what's substitute 0 into the marginal abatement cost or into the E, for example, and you get the, this point in here, for example, if you put equal to 0, right? So you're going to get 20, right? And then you're going to get 40 if you put it, sorry, you can't see that, if you put it here, right? But you know how to do this stuff. Anyway, what's going on here? So you have these two lines here, the green one and the purple one, and you see what's the marginal abatement cost for each firm when each one of them has 4 permits, right? So for firm A, right, their marginal abatement cost at this point in here when they're allowed to emit 4 is actually equal to 12. Right? You can just plug E equal 4 into the marginal abatement cost and you get 12. For firm B, actually, if you do the same exercise, you get 24. So clearly, the marginal abatement cost is not the same for these two firms. So maybe, firm B would be willing to buy some permit if it's less than 24, right? From firm A, as long as firm A will be happy to sell for more than 12. Okay? And these kind of trade between themselves, this is the gain that we will get from trade. Okay? So let me kind of show you that in a slightly different way. So what's going on here? So basically what I did here, I just drew exactly the same thing that I have before. I just put it all together. Polluter A and B, right? The purple and the green line. And I also created the economy-wide aggregate marginal abatement cost, right? So it's this red here, okay? So the purple go all the way here, but I just kind of put the red on top of that because this is the aggregate marginal abatement cost. Now, the cap that you calculated for me is 8. Right? So this is what we have. We're starting with this position here, that each one of them has 4, right? So they can each, 4 permits, so each one of them can emit 4. So what do we get? So if both of them, so if, as we showed before, that means that the marginal abatement cost for firm A, I think it was, A is equal to 12, and for firm B is equal to 24, okay? But they can sell to each other and potentially benefit from that. And they're gonna sell one, let's say, so the green one, right? So MAC, firm A will sell it to firm B. So now firm A will have 3 permits, and firm B gonna have 5, right? But even at this point in here, the marginal abatement cost is not the same anymore, right? So firm A gonna sell another one, so they're gonna be here. So they're gonna have only 2 permits, and it's still beneficial for firm B to buy one more, so they're gonna buy one more. And then at this point in here, so they're gonna move here, sorry. By this point in here, when they have 6, and firm A has 2, at this point in here, their marginal abatement cost is equal to each other. So they have no incentive to move anywhere else. Okay? Why? Because the price, okay, is equal to 8. Okay, the price of the permit is going to be equal to the marginal abatement cost at E cap, which is here. So each firm, think about there are more than firms than that. Each firm will think, what is better for me, to buy a cap, to buy a permit or to pay abatement cost? So as long as the price of the permit is lower, right, than my abatement cost, I want to buy the permit. And that's exactly what's going on with these guys here, right? So they started here. The price is here. It's cheaper for me to buy the permit. Still expensive for me to abate. So I buy one. Still cheaper for me to buy the permit than abating, so I'm going to buy another one. It doesn't make sense to move here because it's just cheaper for me to abate. And for firm one, for firm A, when they started here, look, I can keep the permits, but actually it's cheaper for me to just abate myself, right, and sell it and get 8, right, because my abatement is less than 8. So if I sell 1, it still makes sense. If I sell 2, this is kind of when it stopped making sense after that, actually, right? So I'm not going to sell 3. But the point here is that both of them gain from this. And these triangles show that. Go ahead and shade the triangles. Show that, how much they actually gain from that. So going back to command and control regulation, basically what we did before, we said, okay, you have this guy here, you have 4 each one, but you can't trade. But they totally want to trade. Why do we want to restrict them from trading? It doesn't make any sense to me. It's mutually beneficial. And it's absolutely helping society as well. So it just doesn't make sense. Okay? That was my point. So it's kind of nice to put it together, actually. Okay, so, so this is basically what I want to show you. Another way to do that, actually, is to kind of think about it in terms of supply and demand. So the demander here definitely going to be polluter B, right? And the supplier going to be polluter A, right? So they have a better marginal abatement cost, so they will sell, right? So why do I do, for example, that it's not going to be more than 6 in terms of demand? Anyone knows, by the way? Because, yeah. Well, here it's supply and demand. So here we're just thinking about the prices and the quantity of emission permits. So this is not a marginal abatement cost anymore. It's related to your point, so maybe this is what I didn't get. So basically, if you have 0 abatement, if you invest nothing in abatement cost, then, let's go back, right? Then essentially you're going to have, it's going to be 10, actually, right? Your emission is going to be equal to 10. But this is what I show you here, right? EB equal 10 and EA equal 10. You can just basically put it in MAC equal 10 into this function. This is what you're going to get. This is how I get this interception here and here. My point here is that, if at the maximum you're going to have 10 and you already have 4, you're definitely not going to have a demand more than 6 to buy extra. That's my point. Okay, 10 minus 4 equals 6. And in terms of supply, you can't supply more than 4 because this is what you got. So you don't have more than 4 permits. Right? Basically, the point here is that they continue to sell to each other until supply equal demand, right? Which is basically 2 units that they exchange between themselves. It's exactly the same thing that I showed you before, just with a different diagram. Right? That's the point here. And by the way, you can calculate P star. P star is going to be equal 16. Okay, and you can totally do that from all the information that you have here. Basically, you just add the 2 marginal abatement costs together, MAC A plus MAC B. You said that you put these 2 equations together, you add them, and instead of writing MAC A plus MAC B, write total MAC, right? That's going to be equal to 20 minus 2E plus 40 minus 4E. And then you know what's the cap. You replace total E by 8, and then you solve that. And you're going to get P equals 16. Okay, try it at home. And if you can't do it, tell me in the seminar. I'll do it on the whiteboard very quickly. Okay, but it's better that you try at home. Okay, so this is kind of what I showed. So basically what I'm showing you now and what I showed you is that we get static efficiency, okay, with cap and trade. That's great. We get the desired level of pollution at the least cost. Now let's look at dynamic efficiency. I think this is what you were talking about before. Okay, So let's say that I need to buy all the permits. Okay, you can do it in different ways. Let's say I need to buy all the permits. Okay, so I need to go to under, let's say, MAC1. Okay, I need to buy. What do I need to buy? My abatement cost is going to be A plus B. Plus, I need to buy 0 to E1 times P permits. So let's say that this white square here is E, so I'm going to have to buy permit. The cost of permits that I'm going to have to buy are going to be equal to E plus C plus D. Okay? And again, abatement cost is going to be A plus B. Okay, if I have MAC1 at the moment. Okay, this is where the permit price is going to be. Okay. Okay, now, under marginal abatement cost 2, right, let's say that I don't move, right, so I need to be here. What's going to be my abatement cost? Well, it's just going to be, what's that going to be? What am I going to do, actually? Someone tell me, what's going on here? Do I have an incentive to move to marginal abatement cost 2? Yeah. E what?
The E, the box E.
Sorry, P time E2? Yeah, right? Because I'm going to think about what is cheaper for me, to buy the permit, right, or to abate. With MAC2, cheaper to abate all the way up to E2. Okay? So my abatement cost looks bigger, right? Because before it was A and B, now it's B and C. But in terms of how many permits I need to buy P times 0 to E2, which is just E. So overall, I'm going to pay E, C, and B. What's the difference than what I had before is that I don't need to pay A plus D anymore. Does that make sense? So before, with MAC1, I had to pay A plus B for abatement cost, plus C, D, and E, let's say this is E, in terms of permits, right? So the overall was A, B, C, D, E. Now I pay only B, C, and E, so I don't pay A and D. So I definitely have an incentive. Okay? And you can kind of draw marginal damage function and think about how things might change if the government decides to change things as well. But basically, it's going to be the same mechanism that we had before where the price drops. Okay? So that's kind of a nice exercise if you want to do it as well. Basically, the point that I'm trying to show you now is that there is dynamic efficiency here as well, unlike in command and control. I don't know if that's what you had in mind before or not really. Marginal abatement cost. Yeah.
Changes. So wouldn't the policy be reducing the property rights in the market? And wouldn't that be...
Oh, so that will reduce the number of permits. That's what you're saying?
Yeah.
Yeah, absolutely. But that's not so right. So that's what I just said. Maybe try it at home. But basically, let's say where the permit price come from. So you have another marginal damage function that goes here, right? And this is the interception. This is why we set it equal to that, right? This is why we set the cap equal here. Now we set the cap equal to something else, right? It's going to be the interception with the MAC2. So yeah, you might going to have a bigger reduction or less permits, I guess, or something like that. But look at the price of the permit. It's going to go down, right? Think about P prime. Now it's going to be in the new interception of the marginal damage, which is exactly the same marginal damage, but now with the interception, when it intercepts with MAC2. So it's totally going to be beneficial. Because now the price of the permit is going to go lower. Okay? Draw it at home. Again, I'm happy to if you You know what? Even better, I put it on Moodle, this diagram that show you all these things, because I've done it before. I remember that. It's not the first time someone asked me this question. But I think that maybe I will delay it for a few days. Try to do it at home. Just basically draw the marginal damage. Let's say just make it up, right? So like draw it like that it go through here, and then try to calculate all the different areas and see where you know, how it kind of potentially makes sense to go about that. Yes?
I think the incentives for R&D or investing in reducing marginal abatement costs are going to depend on how the permits are being distributed.
We're gonna talk about that. Okay, just we haven't talked about it yet, but yeah, potentially. There is lots of discussion around that. Yeah. Okay. Let me go through a few things. So you're talking about initial some kind of potential complicating and in implementing marketable permits. So we saw that for efficiency, static efficiency. Let me clarify. The initial distribution of permit doesn't really matter, but how do we actually issue them? There are different options, as I mentioned before. One is auction. Polluters not going to like it because they need to pay. Before they didn't pay. Remember, if status quo, essentially we give them the right to pollute, but now they need to pay. They're not going to like it. But so I think that also for political reason, in many cases permits are given away to current polluters. But that also creates lots of problems. For example, that might increase if you don't do it right. We're going to talk on some of these issues in the seminars, but it might raise, bring about higher barriers of entry. This is something that we definitely don't want to do as economists, right? So basically, firms that are already operating get free permits now. New firms that come in need to pay for that. That's a bit unfair and potentially not something that we want to do. But you can totally deal with that in not very creative way, but in quite straightforward ways. Also, there's some issues, for example, in this kind of related to that if you tell you don't want to do that, some people did. So look, from now on, we're gonna monitor you, and for the next year, and we're gonna decide how many permits we're gonna give you based on how much emission you have in the next year. So then firm has an incentive to actually increase emission because they want to get more permits for future periods, right? So you don't want to do things like that, right? You want to go look at historical emission or some other stuff, okay? But there is definitely some issues on around innovation, and maybe you can play with that in such way that potentially provide more incentive for innovation to a certain way. But it's very complicated, and you need to kind of worry about lots of different things. But again, we're going to talk more about that. Dominant firms, this is another issue. If there is a single firm that is very large, it can exercise market power such that under permit system, the attainment of L, the number of permits essentially, would not occur in the least cost way. This occurs when the firm is not price takers in the permit market. So basically they have some strategic reason to, and they know that they can affect the price of the permit market, and therefore they can decide, depends on what works for them, strategically either withhold or sell more than they actually need in order to equalize marginal abatement costs. So this is why it kind of required the assumption of a competitive economy. Market finance, this is another issue. With too few polluters, this is kind of why I mentioned with two, it might not going to work. Market transaction may be infrequent or non-existent. I mean, for those of you with some background in finance, you know that you need some volume of trade sometimes to move things forward. If people just don't trade it, I mean, you might going to be in quite a lot of trouble. But in this point in here, look, at the end of the day, we need this trade. If the trade doesn't exist or not exist frequent enough, we're not going to get the what we're looking for, which is basically allocate pollution abatement or emission abatement in the right way. If we just don't trade enough, it's not going to work. And also, there are other issues around that as well. Everything is in the book. And then the last thing is our friend from before, transaction cost, okay? Again, everything is great, but if you make it very complicated for firms to trade, and it's very costly for them, at the end of the day, they gain these triangles here, remember that? If the cost gonna be more than these triangles, they might as well stay with 4 permits each. They're not going to move. It doesn't worth that. So you need to make sure that trade is, transaction costs are quite low. That's what I'm trying to say here. Okay, so just 2 examples before we take a break. I know you need a break. I need a break as well. It's my second lecture today. Okay, so we're going to talk more about it in the seminar about the acid rain program. So one of the major air pollution problem in the United States in the 1980s was basically the emission of SO2 that led to acid rain, something that you definitely don't want to have. Back then, it was SO2 level were in the region of, I think, 16 to 20 million tons, I think. I don't know if 16 is right. I think 16 to 20. And basically what happened in 1990, there was the Clean Air Act amendment that's signed by George Bush, the elder, so the father of George Bush that you probably know, which basically move away from traditional command and control regulation into, I think, the first big cap and trade system that aimed to reduce SO2 emission from electric utility in the United States. I'm going to talk about it more. You have a whole paper that you need to read about that in your reading week, in your reading list. But it was very ambitious to basically cut it by around 50%. So think about the ambitious here is to cut, let's say, CO2 by 50%. It's very hard, okay? So that was the, and we're going to talk in the seminars about how do they manage to move away from command and control into cap and trade. Also politically, it's very interesting, because there's this misconception among many, potentially now it's slightly different, that, the Republicans are always kind of anti-environment in the US, but actually most of the environmental regulation in the United States came from the Republican Party. But to sell it to the base, it's very interesting how they did that. So we're going to talk about it in the seminar, okay? Again, maybe the Republican Party right now is slightly different, but historically speaking, to be honest, with air pollution and water pollution is not, but with other stuff, it's a bit. But anyway, I'm not going to go political here, but we're going to look at how they managed to use, Republican language to sell this policy, okay? I think that's fascinating. This is why this article is still on your list. Anyway, let me show you some evidence. Basically, very difficult to evaluate the SO2, but because there are different policies that came about together and just after. But overall, I'm going to show you a picture of the emission reduction, which is phenomenal. And then in terms of cost saving compared to command and control, everything was done by around one office at the EPA, maybe 10 people, maybe. All right, so it didn't cost much. In terms of the EPA, there is obviously cost for the firms as well. Right, so this is kind of SO2 emission in the United States across time. So this is kind of the time series data from 1980s to 2014. So I said it was around 16. I think it was somewhere between 16 and 20, I don't know. But anyway, let's say 16, and the aim was to reduce it to something like 8. This is basically the acid rain program. This is acid rain program and CARE. This is kind of another program that also aimed to reduce SO2. And you see that over time, these 2 programs together, this is when you get this orange guy here, this is basically both of them. You see that, it was signed in 1990. Within a decade, pretty much we got a 50% reduction, okay, than what we kind of wanted, or almost that, okay, in 15 years, I would say, all right? So that seems to be quite great. And then you can see that there was a reaction to that, and government then said, oh, actually, we want it lower than that, lower than 8. We want to move towards around 4. This is what this dashed line here means. All right, so we kind of, okay, so firms kind of innovate. We know it's cheaper to do it now. Let's move further, okay? But you see it, in general, if you look at the United States, overall, if you look at PM 2.0, all this stuff being regulated, sharp decline over time. So regulation actually works, okay, which is good news for us. In terms of the ETS, this is from a relatively recent paper by by Antoine, which is a former, still at Grantham, by a former colleague here at LSE, now working at the OECD, and Frank Venmans, actually, they're going to teach you next term, the first 5 weeks, right? And that was published in the Journal of Environmental Economics, and then they kind of look into the EU ETS, into kind of different kind of aspects of that. So this is kind of a very, very simple kind of diffs and diffs setting, looking at ETS installation. Some of them were regulated, some of them are not. Installation, some of them were regulated by the ETS, some of them were not. And you see that before, it's kind of look kind of pretty much the same in terms of the trend. I mean, the ETS installation have a slightly higher level of emission, but then once the regulation hit, you see kind of a reverse of this example. You can also put it in a regression, in terms of the diffs and diffs here and get the actual reduction. We're talking about a reduction of around 10% in emission from this regulation. This is just the ETS. We can talk whether that's good or not. They also, I think, and it's statistically significant, in terms of also they look at the economic performance because they were worried about, maybe that's going to hurt some firms. So they look at what happened to revenues, what happened to fixed assets, what happened to employment, etc. Again, it's kind of looking at the same thing, ETS regulated, non-ETS regulated, and they see that the gap between EU ETS and non-regulated firms seems to widen actually for, for revenue, right? Also for fixed assets and for, I guess, for employment. We don't see any effect on profit really, which is, it's not necessarily like a bad thing that we don't see because we would potentially expected some negative effect, so at least we don't really see that. It is not significant, so this is kind of basically earning before interest and taxes, right? But it's kind of just like, just show you that we can look at emission, but we also want to look at other aspects of the firms that being affected. Right, let's take 8-minute break until 5:10 and we come back, okay? Someone had a question, so you can just come and ask me, okay? Let's go from this here. So I'm trying to see what you're talking about. All right. So why they're not gonna have an incentive? So if I draw a line, right, for here, right, through here, then.
I agree.
You see what I mean? Then I just overall, I mean, it's kind of what you did. So this is why it's kind of.
But that's not what the government is doing, because in the US case, as a train example, you said, oh, they saw it and therefore they reduced the cap. What does the reduction cap induce? An increase in price. And this increase in price is not what you see here. Because like, the economically efficient and the right thing to do is to pay, well, let's keep the cap at the same level to like drive the prices down and then have the incentive structure for the firms. But it's not what the US government did. The US government, I don't know, what the US government was like, oh well.
No, but here we also increase the cap, right? So now we say that if the cap was here, now the cap is going to be here. So we actually need to, we have less permits. Because the efficient level of pollution is closer to zero. So we have less permits. But we still have less permits.
But then what the US government did was like they went too far, way too far.
Potentially.
I think in the paper it said like the price was $2,500 and then they dropped to 500 the
when we have dominant firms. Now,
Yeah.
this one was about, it wasn't like all, it's not like CO2 that we have everything contributed to CO2, right? That was just a few, well, relatively few electric utilities. So that's, is that a competitive market? I don't know. Probably not. So then some firms, maybe big firms, have, I think, potentially
Yeah.
have some incentive to behave in such way that they want to affect the price of the permit.
Yeah.
So then permit price is not necessarily going to go down.
Yeah. Would we?
But yeah,
Would this, like, I think, I hope I understood the point you made. Would this be possible in a perfectly competitive market? Like that,
the price is going to go up.
no, that, like this is the example from the beginning of Cabot Valley where you were like, oh,
This is commodity.
sorry, with command and control. That you said, okay, the firms essentially have the decision, okay, we will do anything, stay up here and say A and B, or we innovate and then do B and C. But this would be then sort of all firms combined, right? Because if I'm just one firm and all other firms go here and I'm like, I'm lazy, I'll stay up here, then you have a big issue.
Yeah, this is just yeah. I mean,
So it would be a one firm limit.
yeah. I mean, you can think about it at once. Okay, so I see a point. So this kind of coming from like this very very simple example of one firm to
Yeah.
multiple firms. You can totally generalize it, and you can say like, look, the point is that once the technology is out there,
Yeah.
that's going to be the new standard.
Yeah.
Something like that.
Okay.
So I definitely want to be on the frontier.
Yeah, exactly.
Yeah.
In the like.
Exactly.
Yeah, thank you.
Oh, why they still gonna? Why? Yeah, 7. Yeah, can I just show you on this? It's gonna be easier for me. Where was I? All right. So here.
Yeah.
So they both started here, right?
Yeah.
Then they have 4. So this is A. Let me just remind myself. Sorry. Yeah, this is A. This is B. Okay. So if they here,
Yeah.
right, it's still cheaper for them to buy the permit, right? This is the permit price,
Yeah.
16. This is the abatement cost.
Yeah.
So the permit price is cheaper than that.
So we have to look the aggregate MAC, but not the individual.
No, individual. Actually, okay, you can go here. At this point in here,
Okay.
right? It's cheaper for them if it's 16, let's say, the price of the what was the price of the permit? I don't even remember. I think it was 16, right? Anyway, I think it's 16. Yes, 16.
Yeah.
So at this point in here, if they're at 5, 16 is less than their marginal abatement cost. So it's cheaper for them to buy. Forget about the economy one. It's cheaper for them to buy the permit
Yeah.
than abate. And then once you cross another one, which is basically to here, this is where the marginal abatement cost is actually equal to 16. And then, so they want to buy it still, but they don't want to move any more to here because here their marginal abatement cost at 7 is lower than the price of the permit. So it's cheaper for them to abate, for example.
Okay.
So as long as the marginal abatement cost is above the permit price, they want to buy.
But for the aggregate MAC, it's like higher than the permit price.
Yeah, we're never going to be in a situation like that.
Oh, okay.
We're never going to be here, right? Because basically, what's going to we're going to end up here, right? So we're going to be in here. We're never actually going to be in 7, in which each one of them. So well, firm A has 2 permits and firm 2 have 4. They're not going to have 5. That's my point. They're not going to have 5 because it doesn't make sense for them to buy extra.
Oh, okay.
Because so they need to, for every unit of emission that they have, they need 1 permit. Right, so they think about how many permits they actually want to buy. So as long as the abatement cost is higher than the the price of the permit, they want to buy it. They don't want to buy more than that. So the trade ends when it's just equal to here, right? So basically, their marginal abatement cost is 16. So basically, they have 6 permit.
Yeah.
Right, this purple thing goes all the way here. This is the marginal abatement cost curve,
Yeah.
and they're going to end up at this point on their marginal abatement cost. The marginal abatement cost at this point is going to be equal to 16. This is when they have 6. Right? We have only 8. The other guys have 2. They also don't want to sell anymore, right? Because if they sell, actually, it's going to cost them more to abate. So you're going to have no supply of that, right? I mean, potentially yes, but they're going to have to raise the price.
Yes.
But given that the price here is lower, it's not going to happen. Does that make sense?
Yeah, yeah.
Okay.
Thank you.
All right. Let's continue. By the way, I didn't show you this table before, but this table essentially what it does is to show you what I just showed you here with the coefficients of the diffs and diffs. So it's kind of the first line that I guess you're interested in. So we see increase in revenue, increase in assets. Not significant effect on employment, actually. I guess nothing major here. And really nothing on profit as well, so it's not statistically significant either. So if you kind of want to, so again, feel free to read the paper if you want. It's nice. It's not perfect. Don't tell Frank. But no, I'm joking. It's a nice paper. Very useful for what we do here. Okay, and there are quite a few papers. By the way, Antoine, the first co-author on this paper, has quite a few papers on the EU ETS. He used to work at Grantham before, so good colleague. All right. Any question before I moved on, by the way? Before moving on, any questions? No. Okay. Just to remind you, you have a problem set for. You had a question, sorry. Not my paper. No, I think that I think it's a bit noisy, to be completely frank with you. What's going on, Frank? But yeah, I can't. I don't know on top of my head. I think that the main point of the trying to sell here is that it's not all. So basically, I think, and you can ask Frank next year, but or when you see him around campus. The concern is, okay, you regulate the environment, right? That's the story, right? You regulate the environment, you get a reduction in emission. That's great. It's kind of what it did in the first part. But then, are you hurting firms, right? I mean, the ETS, especially in the beginning, there was all this exemption list, right? Of basically, firms were saying, look, if you're going to regulate us, they don't regulate us in country X. It's not fair. We're going to lose our competitiveness. So we're going to lose in terms of profits, revenue, and all this kind of stuff, right? We're going to have to lay off lots of people. That was the discussion, right? It's still the discussion among when you're trying to introduce any kind of environmental policy. Well, firms don't want that. Quite clearly, we understand why. They don't want to buy the permits. They don't want to pay the tax. Make perfect sense. So And we're going to talk about it a bit next week because there is asymmetric information involved here because we don't necessarily know if the threats that they make are credible or not, but it looks like it might be credible, right? So what they're trying to do here is they're like, okay, yeah, we see a reduction in emission. Does it actually hurt firms? Let's kind of empirically test that, and it doesn't seem to be the case, at least according to this paper, with this methodology. It's not the methodology. We can talk more about it when we reach the kind of evaluation part, I guess, the estimation part of the course. But what I did here is like matching with diffs and diffs, which is great, but it's in this case, it's very hard, let's put it like that, to get a causal estimate here. But this is kind of what they're trying to sell. Actually, a former student of mine, undergraduate students here at LSE, for the third year dissertation, what they did, that was in 2016. They used this exemption rule. I'm going off topic, but I'm still going to tell you that. It's fine. There was an exemption rule about which, so basically the worry about ETS, the EU ETS is about carbon leakage, things like that, right? So and lose a competitors to other regions around the world. So they create this list based on some kind of factors, whether you have some exposure to other industry in other places, etc., things like that. But at the end of the day, the number, the criteria is somewhat arbitrary. About whether you're going to be in the exemption list or not. So we basically look around this cutoff point, firms that regulate compared to firms that are not regulated in kind of regression discontinuity design, see whether lots of different outcomes that we care about actually work. So it's kind of another way to estimate some of the things that they were interested in, rather than just a diff and this. It's similar, but it's not exactly the same thing. Yeah, it was a great dissertation, and I potentially can share with you. Since then, he actually finished his PhD. This was, I think, one of the best undergraduate dissertation I've ever read. But he was phenomenal. Okay, let's move back to the topic of today. Sorry about that, but it's just amazing students. So I remember I was reading on a flight, and I was like, that is amazing. All right. Okay, so now that you know everything you need to know about taxation, cap and trade, how to regulate the environment, what's the efficient level of pollution, everything you need to know, let's start to talk about further complications, okay, in the use of taxes and permits. Let's start to kind of reduce some of the things that we implicitly assume and see where we get. Okay, so more specifically, today we're going to talk about two things that really have an impact on how we potentially want to think about efficient level of pollution, but also about regulation. One is space. What do I mean by that? If you think about pollution, for example, let's say water pollution or air pollution, what you emit here also can transport, move to another place. So let's say you emit something in central London, it can also reach other parts of London. It doesn't necessarily stay just in London. And the bigger the sources or let's say the entity that generate the pollution, maybe the extent in which space matter is actually bigger. So think about what happened in California maybe 2 years ago it was. Remember in the summer there was a big fire? And the fire that happened in Northern California, even parts of Canada, went all the way to New York. And New York was significantly affected by what happened so many miles away from there. In fact, we got some of the pollution here in the UK. It was tiny, because over space, the atmosphere has this phenomenal ability to clean some of the pollution over space. But it's a real thing, right? So what we emit in one point does also affect other areas as well, okay? So space is a massive thing that we need to kind of think about, okay? It's not with every environmental issue, because with some cases, for example, with CO2, it doesn't really, to the best of my knowledge, but maybe people here have better knowledge of this than I. It doesn't really matter where you emit CO2 in terms of global CO2 but with things like local air pollution or things like PM 2.5 or things like that, it matters quite a lot. Okay, and I'm going to show you evidence for that. In fact, we're going to have a whole lecture on spatial issues, okay, because it's so important. That's something new that we didn't have before, okay? So how space coming in. And then we're also going to talk about time, the time dimension as well, okay? Because some of the, for example, what I just talked about now, CO2, it doesn't matter what we, well, it matters not what we emit now, but it's also matter what we emitted in T minus 1. Okay, because that kind of accumulate over time. And what we emit now also going to affect, you know, T plus 1 and T plus 2, et cetera, because it just stay in the atmosphere for longer. Okay, so we're going to try to think about these two aspects here. We're going to start with space. Again, we're going to talk more about space in a subsequent lecture. But let's start, and then about time, we're going to spend a lot of time, you're going to spend a lot of time thinking about time dimension, specifically when we talk about natural resources next term, okay? Think about, you know, yeah, how we, for example, extract oil from the ground in the optimal way. All right, beautiful slide here that I created. Sorry about that. But hopefully it's going to make the point quite clearly. Right, so what do we have here? So we have this beautiful, beautiful town here that anyone want to live in. And there is a river that's coming into the town, into this small lake, and the lake, let's assume, is the water source for all the residents in this beautiful town, okay? Now, upstream, there are two big, scary, ugly factories that are very, very bad. I'm joking. They create some stuff that we probably need as a consumer, but we don't want to see that, right? How it's all being created. But they do things that we probably buy. But when they do that, they also dispose some of the waste, let's say, into the river. Now the river is upstream for where we are, so it will affect the water quality where we are. So there are two things here, right? Remember that I told you, I think in week 2, that they're going to use pollution and emission interchangeably? We're going to stop doing it right now, and let me tell you what I mean by that. So in terms of the damage at what's being created, what we care about as residents of this beautiful town, assume that no one lives around there, all right, is actually the pollution. So how polluted the water are in this location, okay, when we actually use that. What's going on here, this is the emission. Now, why emission is not necessarily equal to pollution? Because distance matter here, right? So that's what I said before, all right? With distance, in this case with water, for example, the nature has this ability to clean itself. So the further you are, so let's say this firm, if they emit exactly the same amount of waste into this river compared to this firm, their effect, although E is going to be equal, you know, it's going to be exactly the same, the effect of this firm on the pollution here is going to be lower than of this firm. Why? Because they're just further away. And basically what happened, you can think about what we call a decay function. So over space, the effect of the emission decline. So that might change everything, because what we really care in terms of the damages, that's the point. I know it looked like a stupid figure, but it's an important figure or slide. What we care in terms of the damages is the pollution. This is what we really care. And even if both of them emit exactly the same amount, they're not going to have the same impact on pollution. Okay? So we need to think about distance here. So let's say that you decide to pollute very far away from population density. That might not have almost, and if the wind direction going into the right direction, you might going to have almost no impact or non-impact at all on population, compared to a firm that, you know, are closer or because of wind direction actually has an impact on population. Because what really matters is exposure. It's not emission. It's very hard to think about exposure. We're going to talk about more about it when we talk about air pollution, because I'm really obsessed with exposure now, compared to concentration. It's really because this is what happened. This is all the stuff that we care about in terms of the damages come from exposure. So you know, arguably, if there is lots of pollution around me, and I'm just, you know, in my house with lots of air purifiers, whatever, and London is completely polluted, I might not going to be exposed to that. Okay? But that's the point here. And that you know, in terms of the water pollution, so this guy here going to have a smaller impact on the pollution here potentially than this guy here. Okay? So, so this is kind of the point, right? So this is the pollution, this is the emission. I said the damages are in terms of pollution. The cost of reducing emission is actually in terms of emission. It's not in terms of pollution. So we need to think about how we actually want to regulate that, because we have two different things here. You see what I mean? The cost for the firm going to be in terms of emission, because we asked them, okay, you need to reduce emission. But the damages are actually in terms of pollution. So we need to translate these two things here. And the way that we're going to do that, we're going to use something called transfer coefficient that translate the emission at the source. So this is the source that creates the emission. And this is the receptor. This is where the damage is being created. Oh, well, this is where we care about the damage. This is the pollution, okay? All right, so let me kind of, basically what I just showed you today, I'm going to go through a few slides to kind of make the point, and then we're going to look at regulation. We're going to do only one type of regulation today. I think it's taxes, and then you can read. There are slides for the permits as well, but we're not going to do that. I never do that. We're just going to do, I think the first one, and kind of try to think about, you know, whether what we've done so far kind of makes sense or not, on how we can potentially change that. And if not, what's kind of, if it's not the first best option, what's going to be the second best, okay? So, the problem of dealing with spatial effect is very real for pollution control. This is because the function that transforms emission into pollution is not known and likely affected by many things, including distance from emission source to the site of damage. Definition, basically what I said, the source is the point of discharge of emission, a factory. These guys here, these are the sources. The receptor is the point at which we care about the level of ambient pollution or water quality, okay? This guy in here. I wrote here that, well, it's actually Costa that wrote that we don't really know essentially the decay function, but it's not completely true anymore, I would say. So this is kind of like a really, right, so I'll do two things. One, I'll show you what I did for you guys. Here I'm kind of like a bad attempt to look into, I just did it with data here from the United Kingdom about PM10. It's just type of pollutant here. I'm going to talk more about it in week 11. But basically what I did here is to try to show you something that is similar to a decay function, but it's not really that. Basically what I did, I took all the readings, all the station of PM10 in the United Kingdom. I calculated basically the distance between them, and I calculated the correlation between the different you know, between the nearest station, okay? So basically I took each station, I kind of look at the correlation with PM10 to the nearest one, based on distance, and then the second nearest, et cetera, et cetera, et cetera. And then I just basically plot everything together and just fit a line throughout. So this kind of show how you don't really have the source and the receptor per se here, but it's kind of show how the correlation of PM10 across the United Kingdom look like in terms of distance. It's quite a big distance here, but you see that over space, the correlation between stations kind of diminish. That's what I'm trying to show you here, if that makes sense. In later week, we're gonna look at a paper, not by me, by someone else, that actually look at one source and neighborhoods nearby, and they actually look at the exact, the Nikon paper, look at the exact, I think, decay function, and they actually use the decay function as an empirical strategy to estimate something else, which is pretty cool. Okay, so we're going to do that as well. It's one of the papers that I like the most. All right, so let's kind of do it a bit more formally. Okay, so P here is the concentration of pollution at a particular receptor. Let's say the town that we had before. Some receptor J, right? So that's going to be the town. and that depends on some function of different emission from different sources. Here we had before 2 sources, it can be many more, plus some background level of pollution. So it might be that the background level of pollution is equal to 0, or it might be that you have some naturally generated level of pollution in terms of PM10, PM2.5, from sandstorms to whatever, okay? You have here P, which is the, so let me kind of walk you through here, because I already mentioned a transfer coefficient, but this is actually when it kicks in. So in many cases, the physical environment is linear, and that can help us to basically define what I'm going to call the transfer coefficient here. So Aij is the transfer coefficient. What is that? That's basically just translate emission into pollution, okay? So suppose a change in emission from source I, delta EI, results in a change in pollution at receptor J, delta Pj. The transfer coefficient between the source I and the receptor J is defined as the ratio of change in pollution at J to the change in emission at I, right? So this is basically the definition of the transfer coefficient. What allows me to transfer emission into pollution and vice versa. So I can either multiply it or use it in order to normalize something else. But I want to make sure that I can move from pollution to emission. This is basically the definition. So it's delta P over delta E, okay? All right, so let's think about efficiency, okay? So recall that this is basically what we had in the previous slide here. What we want to do, we want to equate marginal damage with marginal saving to the firm. But again, what's the problem here? The marginal saving is relatively to emission, and damages is relative to pollution, right? So we must convert damages to the same unit as emission in order to get the expression that we had before, right? That the marginal damage equal to the marginal saving, okay? So let's MDE here of EI going to be the marginal damage per unit of emission from source I, and MDP going to be the marginal damage per unit of ambient pollution. These are not two different things. These are two different things. One is the marginal damage in terms of emission, the other one is marginal damage in terms of pollution. And AI here, not artificial intelligence, right? AI here in this context, A subscript I, that's what's going to make this movement, okay? From P, from pollution, the marginal damage of pollution, to the marginal damage of emission, okay? So what is efficient? Efficiency requires equating marginal savings, right, from emission with marginal damages, and this must apply to all sources, right? So with I sources, what we're going to get the marginal saving, right, of EI, going to be equal to, well, the negative of the marginal cost, but you don't need to worry about that. So you can ignore this guy here. But that's going to be equal to the marginal damage of emission, or if you have the marginal damage in terms of pollution, you can use the transfer coefficient to equate that. So essentially, you wanted the marginal saving and the marginal damage going to basically talk in the same kind of level. Okay, so it's going to be in the same level, either emission or pollution, and you're going to use the this transfer coefficient here to do that. Okay, and basically what you're going to get and what you want to get is that the marginal cost or the marginal saving, in this case the marginal cost normalized by the transfer coefficient, going to be equal across. This is the equal marginal principle. Don't forget, AM here and AN going to be different, right? Because go back here, these two firms going to have a different impact on pollution here. So this normalization going to help us with that. And that's also going to be equal to the marginal damage. So if you think about it in terms of marginal cost, that's going to be equal to the negative of the marginal damage, but you can totally do that in terms of marginal saving. That's going to just equal to the marginal damage. Okay, this condition defines efficiency, right? Essentially, it's what we said before. It's essentially exactly the same condition that we had before. All marginal abatement costs are going to be equal to each other, and marginal abatement cost is going to be equal to marginal damage. The only thing that I did here is to introduce this transfer coefficient to allow for the fact that in different sources affect the receptor in different way. That's all I did here. Literally, that's all I did here. So if a source has a large impact on ambient pollution, its marginal cost of production control must be larger. This is the equal marginal principal. Okay, so again, efficiency required marginal cost of emission normalized by the transfer coefficient equal across all sources, and the normalized marginal cost must be equal to the negative of the marginal damage, or the marginal damage equal to the marginal abatement cost. It's basically what I just said. All right, let's think about emission fees. How much time do I have? Plenty of time. Okay, now, given the transfer coefficient, we can now determine how emission fee should be structured to yield efficiency. So let's think about, bring back what we did last week, just as a reminder. This is why I don't do the tradable permit, because we just did that. So let's kind of do what we did last week. We're going to think about tax again. But what we want now, we want to tax TI for each firm, where TI would yield efficiency by accounting for the transfer coefficient. Now, essentially, if we don't want any direct loss or anything like that, we actually need different T's, okay? Let me show you that. Now, recall that the firm attempt to minimize direct cost plus fee payment, right? Remember, they want to minimize the marginal abatement cost plus the tax revenue. We talked about that with all the figures last week. In a way, we talked about it today as well. Just in terms of tax revenue, we thought about buying permits. The way that it does that, well, it set marginal cost of abatement, which is a marginal saving essentially, equal, or marginal abatement cost, equal to the fee, equal to the tax. Okay, so you can think about T equal to marginal abatement cost. Okay. We can rewrite efficiency in the following way for all firms, M and N, equalize control costs across firm after normalizing by the transfer coefficient, and the tax is equal to the marginal damage of pollution multiplied by the transfer coefficient for each firm. So all firms face exactly the same emission fee per unit of ambient pollution, but to convert it to emission, we need to multiply by the transfer coefficient. So the point here that if we basically say that we want to generate or decide on the T based on pollution, it means that each firm will have to pay different amount of tax in terms of emission tax, because they affect pollution in different ways, depends on the distance that they are located from the receptor. Yes? Yeah, I think you're right. It's just basically to kind of try to make the point that they might going to have to face different tax level. That's what's my point. Now, so basically what I'm just telling you now that, and this is kind of scary, right? What I just showed you right now. I'm basically saying like, well, it depends on where you are. You need to have different tax rates. I just told you last week the whole thing about tax. You just set a tax, go home, forget about it. Now I'm telling you, hold on, you need to calculate all these transfer coefficient, each firm going to have to go with something else. That complicates things. So that's kind of, something, it's not an undergraduate course anymore. So you need to think about things that's going on right now. So let's think about, sometimes you can totally do that. Again, it depends on the size of the program and what you actually do. Sometimes it's possible. But let's consider a case where it's too complicated to let emission fees vary by location. By the way, it happened in some cases. I think in, where was it? You can think about, in Southern California, what was the name of that? Reclaim, I think, right? So Reclaim was, I think, based on something like that, actually. Maybe some people here know more about Reclaim than I hear. But also, if you think about, in kind of like how you deal with space more broadly, I think you can think about like London low emission zone or something like that, right? Why are you restricted necessarily in central London, right, and not somewhere else, right? Again, it's not exactly what we're doing here, but it also depends on, because it's central London, this is kind of, or in London when there's kind of high population density and lots of exposure going on, maybe, you want to restrict emission over there, right? Compared to, if you're in the countryside and you can just drive and do whatever you want, right? And it's not exactly that, but it's similar, the concept of space. But I think that Reclaim is probably a better example here. Okay. So let's consider the case where it's too complicated to let emission fees vary by location, information too costly, seems unfair, politically infeasible, you name it. Let's think about how inefficient is the application of a uniform emission fee when damages depends on location. Okay? So it's going to be inefficient to a certain degree, but let's see how bad it is. And also, let's think about what we, as a regulator, want to do in the presence of this inefficiency. Okay? I'm sorry, the first 3.5 weeks were like everything is beautiful and, you know, now it's just like a bit more complicated. But let's look at that. Okay, so what do we have here? So we have the marginal saving that we have before, and now let's assume that, because what really happened here is the marginal damage, right? That's kind of changed now because of the transfer coefficient. So they affect the damages in different way. I think this is kind of why I introduced T1 and T2. In a way. So, okay, so basically what I'm trying to say that if we were able to charge a very, like different tax to different firms, for this firm here that have marginal damage E2 here for P2, right? So they affect damages in a certain way. We want to tax them at T2, for example. And for firm 1, we're going to go with T1, right? Where the marginal damage is just equal to the marginal saving, okay? But let's say that we can't do that. We need to come with some kind of a uniform tax. What's going to happen? Well, let's say that we go with the T star here. What's going to happen here? Well, we're going to generate some deadweight loss, right? Because let's look at this guy here, right? If we had perfect information and we had the ability to charge them exactly what we should, we would have been here. Instead, right, with T2. But instead we go with T. So how much pollution they're actually going to generate, right? Are they going to generate too much or too little? Well, they're going to generate too little, right? So ideally, they would generate this amount, but now they're going to generate this amount because they're just going to think about their marginal saving versus the tax rate, right? So ideally, they would be here, but actually, they're going to go all the way here because taxes is actually, the tax for them is actually higher than it should be. So this green triangle, this is the deadweight loss for this firm, or for us, okay? In a way, for us. And the same thing you can think about the other firm, right? So actually, their tax should be higher. We tax them too little, so they're going to over pollute. So we're going to be, so this blue triangle, that's going to be the deadweight loss. Okay? So again, this is not efficient and not ideal. So this colored triangle, this is basically the issue that space generated for us, okay? So what would be the optimal response in the face of that? We're going to try to think about the optimal uniform tax rate that's going to minimize the deadweight loss. Again, there is no single fee that's going to be able to erase these two triangles together. That's not going to happen. We left, this train left. That's done. Not going to happen, sorry. But now we live in reality. We say like, look, we can't do that. What we can do, try to think about, and we're actually going to do that. I don't remember if it's in this week or next week. Problem set, we're going to do something very similar. Try to think about, okay, that's happening. Let's try to think about how we minimize the loss here, okay? So it's kind of a second best approach in a way, if you want to think about it this way. But it's just like, this is still something, and we can solve it mathematically if we have all this information, okay? But it requires some information for sure. Let me say if there is anything else that I want to say about that. Anything exciting? No, there is nothing exciting I want to say about that. Oh, okay, so I didn't notice time. All right. And you know, there is in the book, there is the same thing with marketable, with permits essentially, and as I said before we even started the lecture, or before we even started this bit, we're not going to go for it, but just go for it in your own time. Okay. In the last 5 to 10 minutes that I have, I just want to talk about time a bit. Okay, so far we talked about space. We're going to talk much more about space, by the way, later on, as I mentioned, but let's talk briefly about time. Don't have much time to talk about time, right? I had to say that. The other thing that I noticed, by the way, let's take a little break for a comedy break. Did you notice that the course is 4 to 6 and we teach it from 4 to 6? I found it hilarious. No? Okay. Anyway, let's go back. I was the other day. I was like, "This is fantastic." Okay. Time. No, not good. No. I tested on my wife yesterday. She found it hilarious. But I guess this is why she married me. I don't know. It's kind of markets. The marriage market is efficient. That's what I want to say. So, allocation, perfect. All right. She studied here as well. This is not how we met. But she studied here. Maybe she finds this stuff interesting. All right. Okay. What do we have here? We talk about space, but time is also an issue. Why is that? Okay. Here we're going to we consider something called stock pollutant. What is that? Is that basically the pollutant, or we accumulate the level of pollution over time. Okay, so let's assume that stock of pollution can be written in the following way. So we have ST on the left-hand side, and then where am I here? Okay, and then what is ST? So what is the stock of pollution depends on? Well, it depends on basically what happened last year in T-1, right? Time delta, we're going to come back to that, plus how much we actually emit right now. Okay, this is basically the stock of pollution right now. Now, if delta is greater than 0, then it's a stock pollutant, right? Because if it is 0, basically what happened in whatever, T-1 doesn't matter anymore, and the only thing that matters is what happened right now. So this is kind of what we call a flow pollutant. Now, it's a bit tricky because you can think about it, well, everything can be stock. It depends on the time dimension. Are you thinking about 1 year? Do you think about 1 decade? You can think about 1 day, 1 month, 1 year, 1 millisecond, But you can see why some pollutants will be considered more as a flow pollutants. Let's say pollutants that disappear within hours or days. So most of the local air pollution, so to speak, that we deal with, we think about more of flow pollutants, things like PM2.5 and things like that, right? So we generate them today. Let's say even in massive fire in California, it moves to New York, or whatever, but it disappears within days. Some other things, for example, like CO2, that can stay in the atmosphere for decades. So this is where the delta is definitely greater than 0. Okay, even if you think about it in terms of a year. Okay, so 1 minus delta here is the amount that is naturally disposed of each year. So this is how much nature can clear itself every, let's say, year or whatever t is. Okay, so you can think about it in terms of like related to the space dimension, that it depends, nature can clear itself with space, but it can also clear itself over time. Okay, that's the what you need to think about it. And I mentioned example of stock pollution. Pollutants rather, sorry, it's, SO2, greenhouse gas emission, etc. Flow pollutant, we're talking about things like particulate matters and things like that, right? And basically everything that it's here I already said. Efficiency is defined a little differently now, because why is that? Because if we want to reduce emission, the cost for us to reduce emission is right now. Right? If I want to emit 1 less ton of CO2 into the atmosphere, I need to bear the cost right now. The damages from this emission going to be not just, well, maybe now, but definitely, or most likely more in the future. So we have 2 time dimensions here, so we need to deal with that, right? Because if I'll ask you, how much, what do you prefer? That I give you 100 pounds, I'm not going to give you anything, but let's say I give you 100 pounds right now, or 100 pounds in 20 years, probably want 100 pounds right now because you can take the money, you can invest it wisely, or redistribute the money among your colleagues here if you prefer, or whatever. But you definitely want it now, even if you just worry about inflation and things like that, right? So the same thing, we care about this dimension quite a lot, and we need to be able, like we did with space, to translate one space into another, in the sense of like think about receptor and sources. Here we want to think about how we kind of translate different time, right? The cost and the damages, which occur in a different time here. And this is kind of one way to do that. So what we have here, so we have the net cost, which is basically summarizing from t equal 1 to infinity, to the end of time. And what we have here, this is the cost and the damages, right? Depends on the stock and the emission. So again, the cost is in terms of emission, the damages in terms of the stock. So it's not just what I emit right now in time t, it also depends on what happened before, right? What's going to happen. Beta here is the discount factor for valuing the future, and it's defined as, essentially this expression here, 1 over 1 plus R, which R is the discount rate. Again, CT is the firm cost of reducing pollution, D is the damage function, okay? Social planner want to minimize the net cost. That's what I'm trying to do, minimize the damages, minimize the cost for the firm. We did that before, but not with the time dimension. So to determine the amount of emission at any point in time, we start with an optimal amount today. So we can just differentiate this net cost function with respect to E1, and this is what we're going to get. I'm going to move one slide or two slides forward here, but what's going to happen here, a few notes actually before what I'm going to show you in a second, is that all costs associated with the firm level pollution reduction are incurred in the first period, so that's what I said. So all the costs actually depends in the first period, but the stock of pollution at time t is equal to the sum of previous emission discounted. This is why we need this delta thing, right? Because it's the decay of the pollution over time. Okay, now it's not over space, now it's over time. So this is why we have that. This delta kind of represent this decay function over time. Therefore, what we're going to get this expression here, okay? And what's going on here? This is essentially the marginal cost, right, of pollution reduction, or negative of the marginal cost, or the marginal saving, or the marginal abatement cost, whatever you want to call that. And that's going to be equal to the sum of reduction in damages, which is basically what we get here. Okay, the sum of all the reduction in damages. Okay? Now, future reduction of damages are discounted by 1 beta, right? Beta, if you remember, is the time preferences. It's basically going back to R, the discount rate that we have, and delta. Delta is the persistence of that, right? So it's how long the pollutants stay in the atmosphere. These two things matters here, right? Just give you a few more seconds. How we think about the future in terms of discount rate. Okay, Ben Groom, that's going to teach you next term, is the expert on discounting. Actually, he has some really amazing papers on that, including with Martin Weitzman. I think we're going to talk about Martin Weitzman next week. We're going to talk about uncertainty. So he did a lot of work on that, and there is a lot of work thinking about discounting because we care about things in the future. So what is the right discount rate? But also about the persistent, which is kind of something that we need more from other disciplines to know how long it stays in the atmosphere and what's essentially the decay function over time. That's something that we do much less well as economists. We take it as an input from other disciplines. But with the discount rate, it's something that other disciplines take from us. So I was trying to show you also, what our strength, okay? So basically, what I'm trying to say that we need to think about these damages and the costs in different way because the damages also depends on, on the stock and depends on all these kind of different that I mentioned before. When it comes to flow pollutants, when we talk about local air pollution, things like PM 2.5, NOx and all these kind of different things, it's not really a worry for us, right? So then we just go to the normal stuff that MD equal MS, right? Because basically, we don't really think that the cost of reducing your emission today and the damages tomorrow, it's any, we don't need to discount anything or anything like that. So we don't need to worry about that. But it's just kind of, if you think about climate change, climate policy, you need to worry about all this stuff. Again, you're going to spend a lot of time thinking about the time dimension, okay, in the first 5 weeks of next term. There is also some discussion, very short discussion in your book about temporal variability. So some pollutants, for example, ozone, which is secondary pollutant, there is a lot of change, or it really depends on when you emit, because it's secondary pollutant in the sense that you emit some pollution, and then there is an interaction with UV and temperature that make O3 ozone. So then you have something to think about in terms of like how you come up with a policy to capture this temporal variability as well. But it's a very kind of spatial, very, very spatial case here, that unique case. Let me try to make the distinction between spatial and spatial, which is very hard for me to actually make distinction in English. But anyway, you need to kind of, it's not a big thing, but if you want, you can read more about it in your book. Anyway, that's all I wanted to say for today. We covered quite a lot of stuff. You had a question, you can come after I answer that, even better. Don't forget to at least attempt the problem set, and please try to read the papers that I assigned to you as much as you can. If you can't read the whole paper, at least read the entire introduction for the second paper. That's going to give you almost everything you need to know. But try to read everything, okay? See you on Wednesday. Thank you.
Sir, I also have a question. Like,
Yeah.
When we modeling this kind of econometric problems, like environmental problems, does this relate to the spillover effect when we like?
Yeah, spillover in terms of pollution over space, you mean? Yeah, absolutely. So for example, so let's say that you want to test the, how the low emission zone in London has an impact on whatever you want, on health.
So we have to control the.
Yeah, but if you just look at, for example, think about the diffs and diff setting, right? So you compare the area that is within the LEZ. Then you said, look, I can just look at what is around that is not part of the LEZ. That's going to be my control. And whatever is within the LEZ, that's the treatment. That's something that you don't want to do because you have a spillover. Because it's not that pollution stop at the border of the LEZ. So like, I can't cross the LEZ border. They're definitely going to go into the area around that. So then you need to worry about it because essentially what you have is that the control group is also treated. So there is an impact on your way that you estimate things. So for example, in one of our papers that we have that, we have like a buffer around London that we prevent that, from this area to be a control group. We actually use control group which are further away, okay? So this is one thing. The second thing that you might be interested is like, and this is how we see it, this is also another treatment, just different intensity. So I see the LEZ itself, what happened to this area, but also in the area around it, because maybe there is a positive spillover from the policy that it actually reduced pollution in the area around that, or, and this is an empirical question, that in this specific case, that it's actually increased. Why it might increase? Because, for example, if people cannot enter London with a car, they might just going to go around London in these areas, and then we have more emission around the area of the LEZ, or people trying to find parking or whatever. So you get more congestion, all this kind of different stuff. So this is an empirical question that we try to do. But it certainly have an impact on estimation, 100%, because pollution moves across space. You also need to think about your standard errors, how you cluster them. But again, we're going to do all of that. So you have time. Oh, you can. So when I think about time, another way that I would use that is a persistent. And again, we're going to do something, my paper, and we're going to look at that in terms of how weather or climate change, whatever you want to call that, how that affects economic activity, and say like straight away or over time. So this is what I call persistent. So I don't know what you mean by spillover in terms of time. I see it as a persistent effect. Or yeah, accumulate. Yeah. So yeah, you can see that as well. Yeah. So yeah, you can think about it in this way as well. Yeah, I guess I think about it either accumulation or persistent rather than exact. But I guess it depends on the definition of these different things. For example, with the LEZ paper that we have, we see that the longer, it's essentially the effect of LEZ on student test scores.